This video focuses on the use of a Mathematica notebook to use numerical integration to plot the geodesics of a freely falling massive particle counter-rotating with respect to the source mass of a Kerr black hole. Now, the notebook that I'm going to be using here can be found at this source here, but it has to be modified for the Kerr geometry because this was written for the Schwarzschild geometry. So, and I'll include a copy of the modified one on my YouTube channel, the place where you can link where you can click to find the files. Now, in this series up to now, this is part 4, but in the series up to now, I've been looking at the co-rotating or prograde case. But here I want to focus on the counter-rotating or retrograde case. So we're going to have a particle, which will be a laboratory or any other mass you want, counter-rotating with respect to the source mass of the Kerr geometry. And so let's have a look at that. All right, so a laboratory containing an observer is freely falling in the equatorial plane of a Kerr black hole. In this video, I've always been looking at the co-rotating or prograde case, prograde rotation, but I'm going to focus now on the counter-rotating case, but I'll do that by comparing it with the prograde case. Okay, you can imagine a laboratory here with an observer in it, and they're freely falling in the equatorial plane of this source, rotating source mass here. So here we have a rotating black hole, rotating in the usual positive sense, and this object here, laboratory, spaceship, observer, particle, whatever you want, but an object with mass is going to counter-rotate with respect to the source mass. So in this freely falling frame, the laws of special relativity apply as long as the region of space-time around is kept sufficiently small. That's around the observer. Oops, sorry. And there are two conserved quantities here, the energy, the total energy of the laboratory as it moves along its geodesics, only along geodesics. And this component of angular momentum is conserved. That's the angular momentum around the axis of rotation. Only this component of angular momentum is conserved along geodesics. Total angular momentum is not. Now, fortunately for us, we're restricted only to the equatorial plane. All right, and all that was what I've just spoken about is all in the previous videos. And the past videos, we focused on plotting the prograde or co-rotating orbits in our Mathematica notebook. And so in this video, we will concentrate on the retrograde or counter-rotating orbits. But we'll also compare the two to see the difference, because there is quite a difference. Now, in previous videos, this effective potential has been worked out. All steps, all parts of it have been explained. U is just substituting for the variable 1 on R, the radial variable, the radial coordinate. Capital M is the mass of the source mass, the black hole itself, and M is the mass of the laboratory or whatever other massive particle you have. G is the Newton's gravitational constant. H is the angular momentum, and A is the spin parameter, in this case the dimensionless spin parameter of the black hole. Okay, E is the total energy of the orbit. That's the total energy of the laboratory as it moves along its geodesic. And C is speed of light, and all of those are explained. What we're going to do in this video is focus on the case where we make H the angular momentum of the laboratory, in this case, the massive particle that's orbiting the black hole. We're going to make that negative. We're going to give it a negative, so it's going to rotate against the rotation of the black hole. It will go in the opposite direction. In all the previous videos, H has been positive. Now we want to make a parametric plot of the particle's geodesic in the equatorial plane, looking down from above, from the positive direction of the z-axis. This is the integrand here that the notebook will work with. All that's been covered in previous videos. And just give you a look at what the notebook looks like. Here it is. I better go up to the start here. Now this was the modified notebook. It's a Mathematica program to compute and display the shapes of orbits in Kerr geometry. It's a modification of the Mathematica notebook published with James Hartle's book, Gravity: An Introduction to Einstein's General Relativity by Addison Wesley, 2003. Excellent book. Okay, so with that book came this notebook for the Schwarzschild case, and all I've done is just modify it. Okay, Kerr radial coordinates measured in units of m, so m equals 1. U equals 1 and R, I've explained. In the notebook here, the notebook uses L for the angular momentum. On the slides, I'll just call it H, simply because it looks it's more easy to recognise. The total energy, big epsilon, is this, and the starting radio RST is this. Number of orbits computed, if necessary, is an orbit, and that can vary from 1 up. It's a matter of setting the orbits. You have to make sure the parameters are set so the orbit is classically allowed and doesn't start at a position where the value of the effective potential is greater than E. You can put these units in, the speed of light, something like that. It's just easier to work in unit, convert all the units to 1, and then you're just talking about angular momentum per unit mass. Okay, but you can do that. The stationary limit surface for a Kerr black hole is 2 gm on c squared. The outer event horizon is this value here. Okay, you set the potential. Now this can be applied in Newtonian and non-Newtonian cases, just a question of what you choose the sign to be. Set it equal to 1 for general relativity, set this to 0 for Newtonian potential, and so on. Okay, so here's the effective potential I was talking about earlier. Okay, here's the angular momentum L. Now this is 4.45 units per unit of mass, because the actual, if you were to put the mass M, the true mass of the laboratory here, small m, and the mass of the black hole here, then the angular momentum of the laboratory will be truly enormous, as these things are. But here we're working in units of 1, so per unit of mass. We plot this, and so on, but I'll come to this afterwards and show that as my last example. But anyway, so let's move on a bit. Okay, so let's compare some cases. So we've covered this in previous videos. This is the effective potential for a bound prograde orbit with H is plus 4.65 units, E is minus 0.01. Its starting position is 40 units, so 40 gm on c squared, or just 40 units in this case here. An orbit is 1. Now here's the effective potential in the positive case for this. Here's our energy set here, just below the 0 value, so its total energy is negative, bound orbit. Now the effective potential, if we now want to look at the opposite case where the laboratory rotates in the opposite direction, we put H as minus 4.65, and E is kept the same starting location, 40 units from the origin, an orbit is 1, and here's our effective potential. Putting in a negative H has completely altered our effective potential. It's still got a similar shape, but the maximum has been reduced considerably, as you can see here. And that's simply the effect of putting in a negative angular momentum. It's changed the effective potential considerably. So what do the orbits look like in this case? Well, as we saw in previous videos, here's the prograde orbit starting from out here. That's one orbit. Here's the retrograde orbit starting from here and going the opposite direction. A bit more complicated looking, isn't it? Just like the effective potential was changed. That's n equals 1. Let's go to n equals 2, second 2 complete orbits. Prograde case, in we go, around we go, we start to see precession happening. Precessing of the orbit occurring. The retrograde case, 2 complete orbits, and we see, again, quite complicated looking. Here's the case for 3 complete orbits. You can see the precession as we expect in general relativity, bound orbits precess. And we can see that happening. In the retrograde case, we can make it out too. Same, there's movement there. It's not describing a circle anyway. Those circles are possible. Okay, here's the effective potential of a prograde scattering orbit, beginning far off and ending far off. H is plus 4.65, E is plus 0.1. Here's the effective potential. And again, now here's for the negative case, for the retrograde scattering orbit, by simply changing plus 4.65 to minus 4.65. And the effective potential, as explained earlier. See the difference there? Let's have a look at what the orbit looks like. Okay, so here's the prograde case coming in from the right, around and scattering off. Here's a retrograde case coming in from the right there, going the opposite direction and out again. And scattering. Effective potential for a prograde plunge orbit. Again, 4.65 units of angular momentum per unit of mass. E is this. There's the effective potential. There's E. And have a look what happens here. Effective potential has dropped off again, as you can see. All right, here's the prograde case. As we've seen in previous videos, in it comes, winds itself around quite closely before plunging in through the event horizon. The blue line marks the outer event horizon. The stationary limit surface, or limit of infinite redshift, or surface of infinite redshift, is further out than here. It actually goes out to this marker here where it says 2. So it's actually 2 units. So anything near that stationary limit surface, once it enters that stationary limit surface, it must co-rotate with the black hole. Even if it starts off with a negative angular momentum, it starts off with angular momentum in the opposite direction. Once it reaches that stationary limit surface, it must co-rotate with the black hole. Now, here's the retrograde orbit. Comes in here and plunges straight in. There's no winding in this case. Very little, almost no winding. There's a little bit here, but of course the rotation is counterclockwise, so it's going round this way of the black hole. That's the rotation of the black hole is this way. And so as this comes near the stationary limit surface, it must co-rotate with the black hole. So there's not going to be this winding here, as we see in the prograde case. All right, and another example of a retrograde plunge orbit, minus 4.65. Okay, here we are. Here's the effective potential, and coming in here now. This winding occurs far out from the stationary limit surface, because the stationary limit surface is that mark here, just in the middle of my marker here, right there. The blue line marks the outer event horizon, which is inside the outer stationary surface limit here at 2, or surface of infinite redshift there. And so the winding occurs far out from that, because as it approaches stationary limit surface, it becomes increasingly difficult to rotate opposite to the direction, or to move or to orbit in a direction opposite to that of the rotation of the black hole. And when it reaches that limit there, where the stationary limit surface is defined, at that point there, 2 units, nothing can rotate, not light, nothing can rotate against the rotation of the black hole. It must co-rotate with the black hole. So even light comes to rest at that point there and must rotate with the black hole. Okay, so the winding that occurs in the prograde case, which is quite close, is not in the case here for the retrograde. In the retrograde case, this winding, which is in the opposite direction of the rotation of the black hole, occurs further out, because as it gets right in close, as it approaches that stationary limit surface here at 2, R equals 2 units, 2 gm on c squared, it must co-rotate with the black hole. Right, the effective potential of a prograde fallback orbit. As in the previous video, here's our effective potential. Now here's the retrograde case here, effective potential. And what do the orbits look like? Okay, in the prograde case, we're starting here, falling back in, and starting here on the left, falling back in. Here in the retrograde case, we're starting here and falling back in, but again, further out, but still falls in. That's the only real difference between the two. This arc perhaps covers a greater region. This just covers 2 quadrants. This one covers 2.5 quadrants, and does go further out, and then drops back in, if at all possible. Anything closer here would drop straight back in much sooner. Okay, and here's another one of a prograde orbit, but counter-rotating, again much further out until it reaches here, the stationary surface limit, straight in, bang, the event horizon. It's not going to counter-rotate. Once it crosses that line here, R equals 2 units, it must co-rotate with the black hole. There's none of this winding in any closer. It can't do it, unlike the prograde case. Now, I think I had one more to look at. Yes, there was one more to look at, and that was this particular case. Again, minus 4.45 units of angular momentum per unit of mass. Total energy set to 1. That's the effective potential there. And down we come. Well, I put 6 orbits here. It doesn't really matter. The beautiful thing too, this program is very well written. It's amazing. It's got tests for bound orbits, tests for orbits coming from and going to infinity, the scattering ones, tests for the fallback orbits, and tests for the plunge orbits. And they help you set your values. If you're not sure what values to use, just have a look at these. They'll help you where to place your starting position, your total energy, and so on. Here's the integrand, all explained in a previous video. This is the param that deals with the winding around, depending for bound orbits. And then here is the part that plots the parametric plot. And remembering you need spheroidal coordinates, oblate spheroidal coordinates, where you have r squared plus a squared, square root of that times the cos of the angle. Same with the sine. Displaying the results down here. Now here is this particular plunge orbit. Okay, now the black hole is rotating anti-clockwise, so it's going around the direction in which I'm moving now. And the particle is counter-rotating. It falls in on this plunge orbit. It doesn't last very long. Remember 2 here, this mark here marks the stationary limit surface. So once it crosses that, very much straight in. All right, I think that's what we got there. And that's it, done.